What if somewhere out there, the universe simply forgot to build? What if there's a place so large, so eerily silent that entire clusters of galaxies are just missing? Not destroyed, not hidden, simply never there. What if you looked up at the night sky and saw nothing? No galaxies, no glowing threads of the cosmic web, only endless blackness. What if this emptiness wasn't a small gap but a vast hollow, stretching hundreds of millions of light years across? A place where the universe itself seems to fall silent. Why does this void exist? Why here, and not everywhere? What does it say about how the cosmos was born? And what if we're closer to a void than we think? Its name is Boötes Void. Astronomers call it the Great Nothing, and it may hold answers to questions we haven't even learned to ask. In the early 1980s, astronomers were trying to draw the largest map of the universe ever attempted. They pointed their telescopes into the northern sky, gathering faint glimmers of light from distant galaxies. Each tiny point was a coordinate, a piece of a cosmic puzzle stretching across billions of light years. This survey was supposed to reveal a web of galaxies' dense clusters connected by delicate filaments, like the scaffolding of creation itself. But then something appeared on the map that shouldn't have been there, or rather, something didn't appear at all. Where thousands of glowing points were expected, there were only a few scattered dots. It was as if someone had erased a piece of the cosmos with a silent brushstroke. This wasn't an error in the instruments. It wasn't a cloud blocking the view. It was real. The team led by astronomer Robert Kirshner was conducting a redshift survey, a method that measures how far away galaxies are by how much their light has been stretched by the expansion of the universe. And this gap wasn't just a void on a photograph. It was a sphere of space more than 330 million light-years across. Inside it, where tens of thousands of galaxies should have been, they found only about 60. To grasp what that means, imagine drawing a map of Earth and discovering an entire continent missing. Not an ocean, not a desert, just an empty hole where the land should be. That's what the Boötes Void looked like, a colossal absence in a universe that was supposed to be uniform on large scales. This discovery sent a shockwave through cosmology. For decades, the standard model of the universe had assumed that matter, when averaged across large enough distances, is distributed evenly. The cosmic web would have voids, yes, but nothing this clean, nothing this vast, and certainly not something that seemed to defy the statistical rules of structure formation. At first, some thought it was a mistake, an artifact in the data, but the measurements were solid. Follow-up surveys confirmed it again and again. The Boötes Void wasn't going away. It was out there, silent, spherical, and almost empty. The more astronomers looked at it, the stranger it became. Why would the universe carve out a region so smooth and so huge? Why did it seem to stand apart from the tangled structure around it? And most unsettling of all, how could a place like this even exist? What began as a simple mapping project had uncovered something far more profound. A void so big it rewrote our understanding of how galaxies gather, how matter flows, and how the early universe set the stage for everything we see today. At first glance, the universe looks chaotic. Galaxies seem scattered at random, stars burn in every direction, and space stretches into a cold and infinite void. But when you zoom out far enough, the chaos begins to form a pattern. The cosmos is not a uniform cloud of stars. It's a vast three-dimensional network, a cosmic web. This web is made of thin filaments of galaxies stretching like glowing threads across space. Where these threads meet, they form knots, dense regions we call clusters and superclusters, and in between them lie the voids, enormous bubbles of near emptiness, the dark spaces between the bright scaffolding of the universe. This structure didn't happen by accident. It was written into the universe from the very beginning. Moments after the Big Bang, tiny quantum fluctuations caused some regions to be just a little denser than others. Those slightly denser patches pulled in more matter, growing over billions of years into galaxies and clusters. The underdense patches were left behind. As the universe expanded, they grew larger and emptier, forming the cosmic voids we see today. If you could hold a 3D map of the universe in your hands, it wouldn't look like a starry sky. It would look like a sponge or foam, bright filaments outlining a vast network and enormous hollow cells between them. These voids are not mistakes in the fabric of reality. They are part of its architecture. Typical voids stretch about 30 to 100 million light-years across. They are irregular, uneven, and often laced with faint filaments inside. But the Boötes Void is different. It's nearly spherical, clean, and unimaginably vast, more than 330 million light-years in diameter. Compared to ordinary voids, it's like a cathedral carved out of the cosmos, an anomaly that stands out even among the natural hollows of the universe. This is why its discovery was so unsettling. The existence of voids is expected. The existence of one this big and this empty is not. The cosmic web tells us that matter flows like a slow river through space, streaming along dark matter filaments, gathering in luminous knots. But inside the Boötes Void, the river never formed. The threads never met. The universe simply left a blank space where a cluster of galaxies should have been. Understanding this pattern, filaments, clusters, and voids is like reading the blueprint of the cosmos. It tells us not just where galaxies are now, but how they grew, how gravity shaped their paths, and how the earliest whispers of creation still echo in the structure of space. The Boötes Void isn't a scar left by something that destroyed galaxies. It's the opposite. It's a region where galaxies never formed in the first place. A place that was empty from the very beginning, shaped by the first breaths of the universe itself. Right after the Big Bang, the cosmos didn't expand smoothly. Microscopic fluctuations in the quantum fields made some regions denser than others. These tiny ripples, created during the violent surge of cosmic inflation, were the blueprint of everything that followed. The dense patches grew into galaxies, clusters, and filaments. The less dense patches were left behind, thinning out even more as space stretched around them. Over billions of years, the difference between those regions became dramatic. Gravity pulled matter toward the filaments, feeding the bright scaffolding of the cosmic web. Meanwhile, the voids grew emptier, not because something carved them out, but because the rest of the universe grew around them. But that still doesn't explain why Boötes is so empty. Most voids still have filaments threading through them, faint chains of matter connecting the outskirts. The Boötes Void is different. It's clean. Too clean, one idea points to dark matter. This invisible form of matter acts as the scaffolding on which galaxies are built. If a region lacks dark matter, there's no gravitational anchor to pull ordinary matter together. No galaxies, no stars, no clusters, just emptiness slowly stretching wider with time. Boötes Void might be one of these rare dark matter deserts, places where the cosmic structure simply never took hold. Another idea looks even further back into the inflationary era itself. During those first fractions of a second, some regions of space may have expanded just a little faster than others. A slight difference in how inflation played out could have permanently diluted the matter in that region, leaving behind a vast quiet bubble that never caught up. In that scenario, Boötes Void isn't a random anomaly. It's a fossil from the universe's birth, a frozen echo of the quantum chaos that shaped everything. And then there's dark energy. This mysterious force is accelerating the expansion of the universe. Some researchers have suggested that certain voids may be expanding slightly faster than the rest of space, making them grow larger and emptier over time. Boötes might be one of those places, a cosmic bubble being stretched apart by the very fabric of spacetime itself. Each of these ideas paints a picture of a universe with structure and silence. A universe that didn't build evenly everywhere. A universe where some regions bloomed with galaxies and others were left as untouched voids, relics of a beginning we barely understand. Boötes Void isn't just a hole in the map. It's a memory, a whisper from the first moments of time still etched into the structure of space. Boötes Void isn't the only hollow in the universe. In fact, emptiness makes up most of the cosmos. If you could zoom out far enough, you'd see that the glowing filaments and clusters of galaxies, everything we consider the universe, are just the delicate outlines of a much larger structure. Most of space is not filled with light, it's filled with silence. Across this silent landscape, astronomers have mapped many voids. Some are shallow, some irregular, some stretching across unimaginable distances, but none of them are quite like Boötes. Take the Eridana supervoid. It lies about 1 billion light-years away, and may be linked to a mysterious cold patch in the cosmic microwave background, a faint fingerprint from the early universe. It's large, possibly spanning up to 1 billion light-years, but its edges are messy, its interior still threaded with filaments. It's not a perfect void, more like a ragged wound in the cosmic web. Or consider the KBC Void. This one is closer to home. Some researchers believe our own galaxy might be sitting near its centre. The KBC Void is enormous, nearly 2 billion light-years across, but it's not nearly as empty. It's more of a low-density basin, a dip in the cosmic landscape, rather than a clean hole. These regions are impressive, even unsettling. But Boötes stands apart. Boötes Void isn't the largest by diameter. What makes it extraordinary is its clarity. Its interior is astonishingly clean, almost completely devoid of galaxies, with only about 60 lonely islands of light scattered inside a sphere 330 million light-years wide. That's far below what cosmological models predict for a region of its size. It's as if someone pressed a perfect sphere into the fabric of the universe and left it untouched for billions of years. Most voids blur into their surroundings. Their edges are fuzzy, their boundaries unclear, but Boötes is sharply defined, like the negative imprint of something missing. When mapped on redshift surveys, it doesn't look like a gradient, it looks like a hole. This is why astronomers can't ignore it. It doesn't just fit into our picture of the universe, it challenges it. If the cosmic web is like a living structure, Boötes is a dead cell. A void so extreme that it forces cosmologists to ask difficult questions. Why is it so smooth? Why is it so empty? And what if anything happened here that didn't happen elsewhere? Perhaps nothing at all. Perhaps this is simply what happens when probability stretches to its limits. Or perhaps Boötes Void is telling us something subtle about the early universe, something we haven't fully understood yet. It's not just another dark patch in the night sky. It's the cleanest, loneliest silence we've ever measured. Imagine standing on a planet orbiting one of the few stars inside the Boötes Void. The night sky stretches overhead, vast and silent. But unlike here on Earth, it isn't painted with the soft glow of a galaxy. There's no sweeping river of stars like the Milky Way, no faint clusters glowing at the edge of perception. There is only blackness. The closest galaxy might be tens of millions of light-years away. The next even farther. No thick band of stars, no spiral arms on the horizon. Just a handful of faint smudges scattered across the darkness, so dim they might look like mistakes to the eye. Inside Boötes Void, the cosmos feels different. From Earth, we see thousands of galaxies through even small telescopes. Inside the void, you might see none at all. For a civilization born in such a place, the concept of a vast and connected universe would be almost unimaginable. They might believe their lonely galaxy is all that exists. Their night sky would offer no clues that anything lies beyond. No cosmic web, no crowded clusters, no proof of a greater structure. Even the tools we use to measure the universe, redshift background radiation, distant supernovae, would be far harder to detect in this darkness. Isolation here isn't just about distance, it's structural. The void itself is what separates. Space expands faster when there's less matter to hold it back, meaning galaxies inside the void slowly drift even farther apart over cosmic time. The few that remain become like castaways on a black ocean, unable to ever cross the void to reach one another. This isn't just poetic imagery, it's cold cosmology. The cosmic expansion rate inside voids is subtly different from that in denser regions. The emptier the region, the more freely it grows. Inside Boötes, that means a civilization could live and die without ever knowing the rest of the universe existed. Now think about our own history. For most of human existence, we thought the stars were nearby. We thought the Milky Way was the entire cosmos. It took centuries of telescopes and breakthroughs to discover that we're surrounded by trillions of galaxies. But inside Boötes Void, that revelation might never come. A culture could reach its technological peak without ever suspecting that their cosmic neighborhood is just a lonely island in an endless black sea. This is the quiet power of a void. Not violence, not destruction, but silence so deep it shapes reality itself. Here's a quiet truth that makes cosmology more fragile than it seems. Where you stand determines what you see. Our understanding of the universe is built on light. The faint glow of distant galaxies, the stretching of wavelengths, the speed at which everything drifts apart. We trust these signals to tell us what the cosmos is doing, but what if those signals are shaped, bent, or distorted by where we happen to be? Voids like Boötes don't just sit quietly in space. They change the way space behaves. When a region is underdense, it expands faster than the surrounding universe. Light travelling through it is affected by that extra expansion, like a boat drifting faster in a calm current. From the inside, everything looks as if it's moving away more quickly than it actually is. This is more than a thought experiment. Some astronomers believe our galaxy may lie inside or near KBC Void, a vast low-density region, spanning billions of light-years. If true, this could help explain one of the biggest unsolved puzzles in modern cosmology, the Hubble tension. The Hubble tension is the mismatch between two ways of measuring the universe's expansion rate. One method looks at the cosmic microwave background, the oldest light in the universe, to predict how fast space should be expanding today. The other measures the redshifts of galaxies and supernovae to determine how fast it's actually expanding right now. The numbers don't match. Some suggest the discrepancy may not lie in the physics of the universe itself, but in our position inside it. If we live in a slightly emptier region, then the light we observe is subtly biased by that environment. It makes the universe look like it's expanding faster than the global average. Now imagine a civilization inside Boötes Void. For them, this effect wouldn't be subtle. It would be overwhelming. Every galaxy would seem to race away at breakneck speed, and the cosmos would appear far more desolate than it really is. Their entire cosmology would be shaped by the structure they inhabit. The void would distort not just their view, but their understanding of reality itself. This is the unsettling implication of voids. They're not just empty spaces, they're lenses. They bend perception not by warping light like black holes, but by altering the background expansion of the universe itself. They quietly shift the numbers we build our theories on. So when we draw our maps of the cosmos, we are not neutral observers. We are inside the system, we are trying to measure, and if Boötes Void is any hint, the universe may look very different from another point of view. In the end, emptiness doesn't just shape the cosmos. It shapes our perception of it. When we call Boötes Void empty, it's easy to imagine a place where nothing exists at all. No stars, no galaxies, no matter, a pure vacuum, a cosmic abyss. But that's not what emptiness means in physics. Even in the darkest, loneliest corners of the universe, space is never truly blank. Every cubic centimetre of space is filled with quantum vacuum, a restless sea of invisible energy. Quantum fields ripple everywhere, constantly birthing and destroying tiny pairs of particles and antiparticles. They flicker into existence, collide, and vanish again in less time than it takes light to cross a proton. You can't see them, but their effects are real. They influence how forces behave, how particles interact, and how space itself evolves. On top of that, there's dark energy, the mysterious pressure pushing the universe to expand faster and faster. It permeates everything, even the deepest voids. In fact, voids are where dark energy's influence is clearest because there's less matter to counteract its push. In a strange way, emptiness amplifies the energy hidden beneath it. And then there's gravity. Even though the Boötes Void contains almost no galaxies, It isn't isolated from the rest of the cosmic web. The structures surrounding it exert gravitational pull, tugging faintly at the few island galaxies inside. The void isn't frozen. It's slowly evolving, stretching and thinning as the rest of the universe expands around it. This is what makes cosmic voids so fascinating. They're not silent because nothing happens. They're silent because everything that happens there is subtle. The loud drama of star formation, galaxy collisions and black holes doesn't play out here. Instead, the void hums with the faint rhythm of quantum fields and the slow drift of spacetime itself. Boötes Void is a perfect stage for these hidden forces. No bright galaxies to interfere, no dense clusters to drown out the whispers. It's one of the purest places in the universe to study what lies beneath the scaffolding of reality itself. When you look into this void, you're not seeing nothing. You're seeing everything that remains when almost all else is gone. The Boötes Void isn't just an empty space in the present. It's a relic of the past, a silent witness to the moment the universe was born. Most of the structures we see today, clusters, filaments. Superclusters are the product of billions of years of gravitational evolution. Galaxies have merged, stars have formed and died. Matter has flowed like rivers through the cosmic web. But voids are different. They've changed the least. Because they're so underdense, there isn't enough gravity inside them to stir things up. No great flows of matter. No massive collisions. They quietly preserve the initial conditions laid down just after the Big Bang, making them some of the most pristine regions in the universe. In that sense, Boötes Void is like a fossil, not of bones or rock, but of space-time itself. It may still carry subtle imprints from the era of cosmic inflation, the brief moment when the universe expanded faster than the speed of light and quantum fluctuations were stretched to cosmic scales. Those fluctuations seeded everything, the filaments, the galaxies and the empty spaces in between. While the dense regions evolved into bright, complex structures, the voids remained like untouched canvases, and the larger the void, the closer its structure reflects the universe's earliest blueprint. That's why scientists pay such close attention to places like Boötes. They're cosmic time capsules. Studying these voids allows cosmologists to test the deepest layers of theory, how inflation worked, how dark matter first gathered, how dark energy began to stretch space, and whether the laws of physics have always been the same everywhere. Boötes Void, with its sharp edges and near-perfect emptiness, stands out like a giant fingerprint pressed into the fabric of reality. It may be telling us something subtle but profound, something written in the first fractions of a second after time began, in a universe filled with explosions, collisions and chaos. It's strange that the quiet places can speak the loudest, but sometimes silence preserves the truth better than noise. Boötes Void doesn't just show us where galaxies aren't, it shows us where the universe came from. We tend to look at the universe through its brightest places, the stars, the galaxies, the swirling clusters that paint the night sky. We celebrate what shines the fire, the light, the motion, but sometimes the most powerful story isn't told in the places where things are, it's told in the places where they aren't. The Boötes Void is one of those places, a sphere of silence so vast it could swallow thousands of galaxies whole, and yet it sits there untouched, invisible, almost forgotten. Not a hole in a picture, a hole in existence. This void doesn't roar like a black hole, it doesn't burn like a star, it simply waits. A fossil carved into space-time holding the memory of a universe still learning to build itself. And somewhere within this great lattice of light and silence, our galaxy may sit too. If we truly are living inside a void, it's not just any empty patch of space. It has a name. Astronomers call it the KBC Void, after Ryan Keenan, Amy Barger and Lennox Cowie, the scientists who first outlined its existence. And what they found sits uncomfortably close to home. The KBC Void isn't out at the edge of the observable universe. It isn't hidden in some distant constellation. It is here wrapped around the Milky Way itself. When astronomers mapped the distribution of galaxies and compared local densities to the cosmic average, they saw something strange. The region surrounding our galaxy seemed thinner, the filaments less crowded. The density of matter, both visible and invisible, appeared lower than expected. Not empty, but underdense. And not just by a little. The KBC Void spans an astonishing 2 billion light-years across, making it one of the largest known underdensities in the observable universe. Yet unlike Boötes Void, it isn't a clean bubble with sharp edges. It's more like a vast cosmic basin sloping gently outward, a soft depression carved into the distribution of galaxies. To someone living inside it like us, this basin is almost invisible. From Earth, the night sky looks full. The Milky Way gleams bright, surrounded by billions of galaxies we can observe with modern telescopes. Nothing about this view screams void. But on the scale of cosmic structure, it's as if we're standing in the middle of a wide, shallow valley. The highlands of denser galaxy clusters lie far away, surrounding us in every direction. This idea was once controversial, and in many ways it still is. How could we be living in such an enormous void and not notice? The answer is simple and unsettling, because from the inside a void doesn't look like emptiness. It looks like normal. If the KBC Void really surrounds us, it wouldn't be obvious to the naked eye. The night sky doesn't reveal underdensities, it only shows points of light. To detect the shape of the universe around us, astronomers had to build tools that can measure not just where galaxies are, but how far away they sit in space. The key lies in redshift. When light travels through an expanding universe, its wavelength stretches, shifting toward the red end of the spectrum. The farther away a galaxy is, the more its light is stretched. By measuring that stretch precisely, astronomers can map the three-dimensional positions of galaxies, not just their directions on the sky, but their depth in space. Over decades, massive redshift surveys built a detailed map of our cosmic neighborhood. What they found was subtle but telling. The number of galaxies per unit volume here is lower than the cosmic average. The threads of the cosmic web are thinner, the clusters farther apart. It's not a hole, it's a soft dip in the universe's fabric. But this wasn't just about counting galaxies. Researchers also measured the flow of matter. In denser regions, galaxies tug on each other with gravity, creating peculiar velocities, deviations from smooth expansion. In void regions, those tugs are weaker, and galaxies drift apart more cleanly. By measuring these motions, astronomers could confirm what the galaxy count suggested. We're sitting in a quieter part of the cosmic landscape. None of this is easy. When you're inside the structure, you're trying to measure. The map can play tricks on you. Distances must be calibrated, motions disentangled, biases accounted for. But layer by layer, the pattern has emerged. A great underdensity, faint but persistent, surrounds us like a cosmic valley. If you could step outside the KBC Void and look back at it from billions of light-years away, what you'd see wouldn't be a hole in the universe. It would look more like a shallow bowl carved into the cosmic web, a gentle dip in the distribution of galaxies so wide that the Milky Way sits near its center, almost without realizing it. Astronomers measure this dip through galaxy counts. When they tally the number of galaxies in each cubic megaparsec, the average universe gives them a predictable number. But here the counts fall short. Not by a tiny margin, by enough to mark the entire region as underdense compared to the cosmic mean. The filaments in this part of space are stretched thinner, like faint threads drawn over a drum of darkness. Clusters are rarer, smaller, and farther apart, where other parts of the universe bustle with hundreds of thousands of galaxies packed into dense walls and knots. Our surroundings are more like quiet countryside between these crowded cities. This underdensity doesn't mean we're floating in nothingness. We still see countless galaxies because the scale of the universe is incomprehensibly large. Even a thinly populated region still contains unimaginable numbers of stars. But compared to the cosmic average, our neighborhood is quieter, lighter, thinner. This matters more than it seems. Because the structure of space, how much matter it holds and how that matter flows shapes how fast the universe appears to expand from within it. Standing in an underdense region can subtly change how we see everything else. We don't feel it. We don't see it. But we're living in a vast cosmic valley, and that valley bends the way the universe looks to us. The universe is expanding. That's one of the most profound discoveries in modern science. But how fast is it expanding? That deceptively simple question has become one of the biggest puzzles in cosmology today. Astronomers have two main ways of answering it. The first looks deep into the past at the cosmic microwave background, the afterglow of the Big Bang. This ancient light carries a fossilized imprint of the early universe, and from its delicate fluctuations, scientists can calculate how quickly the cosmos should be expanding today. This gives a number, the Hubble constant inferred from the very fabric of the young universe. The second way doesn't look at the past, it measures the present. By observing distant galaxies, supernovae and variable stars, astronomers can track how their light is stretched by cosmic expansion right now. This gives a second value for the Hubble constant. And here's the problem. The two numbers don't match. The early universe method says the expansion rate should be slower. The local measurements say it's faster by enough that the difference can't be brushed away as experimental error. This is what scientists call the Hubble tension, a quiet but persistent crack in the foundations of cosmology. Many explanations have been proposed. New physics measurement bias, unknown particles, exotic energy fields. But one idea is surprisingly simple. What if the difference comes not from the universe itself, but from where we are inside it? If our galaxy happens to sit in a large underdense region like the KBC Void, then the expansion we measure locally could appear faster than the global average. Like standing in a valley where the air flows differently, our cosmic location might be bending our view of how space expands. It's a bold idea, and if it's true, it wouldn't just explain the tension. It would mean the very structure of the universe is shaping our perception of it. Imagine standing in the middle of a wide, quiet valley. The wind moves differently here, smoother, less obstructed than in the crowded hills beyond. If you only measured the wind inside this valley, you might believe the entire world is like this. But step outside and you'd find a very different flow. Cosmic voids work in a similar way. In an underdense region like the KBC Void, there's less matter to slow down the expansion of space. With less gravity pulling everything inward, the local region expands just a bit faster than the cosmic average. Light travelling through this valley of low density is stretched more. From the inside, it looks as if the universe is racing away faster than it actually is. When astronomers measure this, light redshifts from galaxies, the expansion of supernovae, the growth of cosmic structures, they aren't measuring from some neutral godlike vantage point. They're measuring from right here in this valley, and that subtle difference can distort the results. The effect is small, but the scale of the void is enormous. Across hundreds of millions of light years, even a small bias can amplify into a measurable discrepancy enough to mimic or contribute to the Hubble tension. This doesn't mean the data is wrong. It means the data has context. Every observation is filtered through the structure we inhabit. Just as the shape of a valley shapes the way sound echoes through it, the shape of the universe around us shapes the way cosmic expansion looks. This is why some cosmologists are taking the void hypothesis seriously. If we live in a gentle underdensity, our measurements aren't neutral, they're tilted. And this tilt could be part of why the universe looks faster from here than it does from its ancient light. When we look at the universe, we like to imagine we're seeing it as it truly is, as if we were standing outside gazing down on the cosmic web from nowhere. But that's a comforting illusion. In reality, every observation we make comes from a single tiny point inside that web. We are part of the structure we are trying to measure. That means our view is never neutral. It's shaped subtly but surely by where we are. If our galaxy lies inside the KBC Void, then every signal we record, every redshift, every brightness curve, every map of cosmic expansion is seen through the lens of that underdense environment. We don't just observe the universe, we observe it from a valley in its structure. This is what cosmologists call observer bias. It isn't a mistake, and it doesn't mean the data is bad. It's simply the recognition that measurements are coloured by context, like listening to a symphony from a single seat in the theatre. The sound is real, but it is also shaped by where you sit. The deeper the void, the stronger this bias can be. If we were inside a denser cluster, the universe might appear to expand more slowly. Inside a void, it looks faster. Two observers in two different parts of the cosmic web might measure two different universes, even though they live in the same one. This is a quiet but profound problem in cosmology. We can map galaxies, measure light model expansion with incredible precision, but we can't step outside the universe to check our work. Our perspective is fixed. Our cosmic seat is chosen for us. Imagine being born on a distant world orbiting a lonely star in the heart of a vast void. Your night sky would look nothing like ours. No glowing band of the Milky Way cutting across the darkness. No crowded fields of galaxies waiting behind the black. Just a few scattered points of light, faint, isolated, and unimaginably far away. From such a place, the universe would feel empty. Your astronomers might look up and see only silence. They could spend centuries scanning the sky and still find nothing but a handful of distant smudges so dim they might doubt they were real. The idea of a universe filled with galaxies, trillions of them, would seem like a fantasy. Their understanding of cosmology would be shaped entirely by that emptiness. In their equations, the cosmos would appear small, lonely, and expanding rapidly away from them. They might think their galaxy is the only one, or that the universe is fading into darkness faster than it truly is. Inside a void, isolation isn't just physical, it's perceptual. Even the tools we rely on to see the universe redshift, surveys background radiation standard candles, would return weaker, rarer signals. The void would veil the true structure of reality behind a curtain of black. And here's the quiet truth. If we really live inside an underdense region like the KBC Void, then we're already experiencing a gentler version of that effect. We don't feel the valley beneath us, but it shapes the sky we see. Our maps, our measurements, even our sense of cosmic scale. All of it carries the fingerprint of where we're standing. A civilization born in a cosmic void would grow up believing in a small universe. Their skies would not hint at vast clusters or glowing filaments. There would be no spiral arms swirling at the horizon, no galactic walls blazing faintly in the distance. To them, the universe would be exactly what they could see. A black ocean with a few lonely islands of light. Their theories would grow around that emptiness. Their science would define the cosmos as something simple, small, and fast-moving. If they measured the expansion of the universe, they would find it racing away. If they mapped the heavens, they would see only a thin scattering of galaxies. Their cosmology would be elegant and wrong. And in a way, this is a mirror of our own history. For most of human existence, we believed the stars we saw were the whole cosmos. Then we learned that those stars belonged to the Milky Way. Later we learned that the Milky Way was just one galaxy among billions. And now some astronomers are asking, what if even this vastness is deceptive? What if we're standing in a hollow, and the universe beyond our cosmic valley looks different from what we think? This is the illusion of a lonely universe. A trick not of light, but of perspective. The void doesn't lie. It simply limits what can be seen. If that's true, then our entire understanding of cosmic scale, our maps, our constants, even our age of the universe may carry a bias, written not in equations, but in where we happen to live. When the idea first surfaced that we might be living inside a vast cosmic void, it landed like a quiet shockwave in the scientific community. It was elegant, almost poetic, a simple local explanation that could help resolve the Hubble tension without rewriting the laws of physics. But not everyone was convinced. Some astronomers embraced the hypothesis. They pointed to the data, the underdensity around Milky Way, the smoother flow of galaxies, the subtle discrepancies in expansion rate. The numbers, they said, fit too neatly to ignore. If you stand in a valley, you should expect to feel a different breeze. Maybe this is exactly what we're seeing. Others, however, saw a different picture. They warned that the data could be misleading. Underdensities can appear in surveys for many reasons. Incomplete sampling biases and galaxy catalogues, even how light bends and scatters across cosmic distances. And crucially, they argued the void would need to be enormous and carefully shaped to fully explain the Hubble tension. A structure like that is possible, but not easy to produce in standard cosmology. Some critics went further. If the KBC Void were as deep and wide as claimed, they argued its gravitational signature should leave stronger marks on the cosmic web. We should see telltale patterns in galaxy flow and background radiation, and while some signals match, others remain ambiguous. The debate is far from settled. Each new survey brings more detail, more galaxies, better redshift precision, sharper cosmic maps. But even with all our instruments, the question lingers. Are we truly living in a cosmic valley, or are we just reading shadows in the fog? In every other science, if you want to understand something, you can step back. A biologist can lift a cell under a microscope. A geologist can climb a mountain to see the valley below. But in cosmology, there is no outside to step back into. We observe the universe from within the very structure we're trying to understand. We're inside the web, floating in one of its filaments, maybe even inside a vast KBC void. We can't move our perspective to a distant cluster and look back. We can't float above the cosmic web to get a clean view. We have only one seat in the theatre and it's fixed. This limitation makes every measurement a puzzle. If we find signs of a void around us, are they real? Or are they artifacts of how light bends, how galaxies are distributed, how we build our models? We can't check by stepping outside to see the full picture. We can only infer, compare, and build ever more careful maps from where we are. That's what makes the debate around the KBC Void so challenging. Even with advanced redshift surveys, precision instruments, and simulations, the uncertainty remains. We're trying to describe the shape of the ocean from inside a single wave. This isn't a flaw in the science. It's a fundamental truth of cosmology. We are part of the system we study. Our perspective is bounded. Our cosmic horizon is both a window and a wall. And somewhere beyond that wall, the universe keeps going, whether it confirms our theories or not. Long before galaxies spun, before stars were born, before darkness even had a shape. The seeds of everything were sown in silence. Moments after the Big Bang, the universe underwent cosmic inflation, a burst of expansion so fast that tiny quantum fluctuations were stretched across unimaginable scales. These fluctuations were like fingerprints impressed on spacetime itself. Some regions ended up slightly denser than average, others slightly thinner. The differences were minuscule fractions of a percent. But over billions of years, gravity amplified those tiny ripples into the vast structures we see today. The denser regions became the filaments and clusters, cosmic cities where galaxies gathered, stars blazed, and matter flowed inward. The thinner regions were left behind, stretching wider as the universe expanded. They became voids, silent hollows between the glowing threads. Voids then are not accidents. They are fossils of those first ripples, the untouched fingerprints of the early universe. Their shapes still carry clues about what happened in those first violent instants of cosmic time. If the KBC Void truly surrounds us, it might not be a strange anomaly at all. It might simply be one of those early quantum valleys grown vast and quiet over 13 billion years. Not a hole carved into the cosmos later, but a place where galaxies never truly formed in the first place. Every void tells a story about the beginning. Each one is a preserved page from a book written before stars existed. And right now, we may be living on one of those ancient pages. Most of the universe has changed beyond recognition since its birth. Galaxies have merged, stars have lived and died. Clusters have formed from swirling rivers of matter, but the voids have barely changed at all. Because they contain so little matter, there's nothing inside them to stir, collapse, or ignite. No great flows of gas, no violent mergers, no storms of light. While filaments and clusters evolved into cosmic cities, voids remained like quiet plains, untouched by the chaos at their edges. That makes them precious. Each void is a fossil not of rock or bone, but of spacetime itself. A preserved imprint of the density landscape carved by cosmic inflation. By studying their shape, depth, and growth, cosmologists can peer back into the first instance after the Big Bang without building a time machine. The KBC Void, if confirmed, would be a particularly valuable fossil. Its sheer scale would make it one of the largest surviving traces of the universe's original structure. Unlike dense clusters which have been shaped and reshaped by billions of years of gravity, a void carries the clean signature of its birth. Every ridge around its edges, every filament that skirts its boundaries tells a quiet story, of fluctuations stretched across space of galaxies that never formed of a cosmic map drawn long before any light existed. When we look out into the darkness and see a void, we're not just seeing an absence. We're looking at something that has been waiting there since the beginning. If we truly live inside a cosmic void, then the way we see the universe isn't just slightly tilted. It's fundamentally framed by where we stand. Our perspective isn't neutral, it's woven into the structure itself. The entire Hubble tension debate might be less about new physics and more about local context. If the region around Milky Way is underdense, then the expansion we measure here is not the universe's true expansion rate. It's just our neighbourhoods. From this valley, the universe appears to stretch faster than it does on average. Not because the cosmos is broken, but because our seat in the theatre is closer to the edge of the stage. This would ripple through every corner of cosmology. Age estimates of the universe might shift. The precision of cosmic distance ladders, how we measure space itself, would need re-evaluation. The assumption that we live in a typical part of the universe long taken for granted would no longer hold. It would also challenge a quiet pillar of modern cosmology, the cosmological principle, the idea that the universe looks roughly the same from every point on a large enough scale. If our location is more special than we thought, then even well-tested models would need to bend. And yet this isn't a doomsday scenario for cosmology. Far from it. It's an opportunity, a reminder that the map is not the territory, that the way we measure reality is bound to where we stand inside it, and that sometimes understanding the universe doesn't mean looking farther away, but looking closer to home. In the crowded regions of the cosmic web, everything is loud. Galaxies collide, clusters churn, stars are born and die in torrents of radiation. Measuring the subtle forces that shape the universe, there is like trying to hear a whisper in a storm. But inside a void, the storm quiets. Voids are some of the cleanest environments in the universe. Their emptiness is not just absence, it's clarity. Without dense clusters to bend, light stir matter, or create gravitational noise, the underlying structure of spacetime becomes easier to trace. That makes voids extraordinary laboratories for cosmology. Here, scientists can study the gentle pull of dark energy, the mysterious pressure driving cosmic acceleration. They can probe the subtle effects of dark matter as it shapes the filaments at the void's edges. They can even test alternative theories of gravity, watching how space expands when it's freed from the weight of galaxies. Because voids evolve slowly, their structure isn't buried under billions of years of violent interactions. Their clean geometry preserves the faint fingerprints of the universe's earliest forces. Every edge, every filament surrounding them is like a line of code written into the fabric of reality itself. The KBC Void, if confirmed, could be one of the largest natural laboratories ever identified. A place not of light and noise, but of silence, where the universe speaks more softly and more clearly. We like to imagine the universe as something fixed and absolute, a vast and impartial reality waiting out there for us to measure it. But the truth is quieter and stranger. The universe we see isn't just shaped by what it is, It's shaped by where we're standing inside it. If the KBC Void truly surrounds us, then our cosmic valley is gently bending every signal we receive. The light from distant galaxies, the rate of cosmic expansion, even the patterns we trace onto our maps of the cosmos, all of it filtered through a landscape we cannot step outside of. We are observers inside the system, not outside it. This isn't a flaw, it's a reminder. A reminder that the universe is not a stage set for us to watch from afar, but a structure we are embedded in a vast living web that defines how we see, measure, and understand everything. Maybe that's why voids feel so mysterious, not because they are empty, but because they reveal something about us, how fragile and local our perspective really is. Another observer somewhere in a dense cluster might see a slower universe. Someone born deeper inside a void might see a lonelier one. Each of us would be looking at the same cosmos and describing a different reality. In the end, this is what makes cosmology beautiful. It isn't just about mapping galaxies or calculating distances. It's about learning to read the universe from a single point inside it, knowing that the story we uncover depends on where we stand. Maybe the universe looks this way not because of what it is, but because of where we are. The unthinkable question. The universe is not eternal, at least not in the way we once imagined. For most of human history, we thought the heavens were fixed, eternal, unchanging, a silent backdrop to the drama of life on Earth. But modern science has uncovered a darker truth. The cosmos itself is mortal. Its brilliance is already fading, and in ways more dramatic than anyone could have foreseen. So here's the unthinkable question. Is the universe already dying? At first glance, the night sky offers no such clue. Stars sparkle, galaxies glow, supernovae erupt with dazzling power. From our vantage point, it all feels alive, vibrant, even eternal. But when we measure carefully, when we peer deeper with the most powerful telescopes, we see something else. Decline. Star formation is slowing. Galaxies are aging. Black holes are awakening in ways that drain the cosmos of its light. Join me today as we travel through time from the fiery birth of the cosmos to its inevitable demise. Along the way, we'll witness the rise and fall of galaxies, the treachery of black holes, and the slow suffocation of all that was ever bright. Our story begins in a paradox. The very forces that once gave life to the universe are now conspiring to extinguish it. The same gravity that gathered gas into galaxies now drags them into collisions that can strip away their future. The same black holes that regulate star formation can, if they feed too greedily, destroy entire galaxies from within. But here's the twist. The death of the universe is not a far-off event. It has already begun. Scientists now believe we live not in cosmic morning, but in cosmic twilight, a time when the golden age of star birth is already long gone, and what remains is only the long, slow decline. How did the universe go from overflowing with new stars to slowly choking on its own silence? To answer that, we must travel back to its most glorious chapter, the peak of creation when the cosmos blazed with light as never before and never again, cosmic noon, when the lights peaked. There was a time when the universe blazed. Astronomers call it cosmic noon, a turbulent era, roughly 3 to 4 billion years after the Big Bang, when galaxies were ravenous and the sky was busy with birth. Gas streamed along invisible filaments of the cosmic web like rivers feeding a growing delta. Where those rivers met at the nodes, galaxies ignited. Back then, star formation was over 10 times the pace we see today. Entire neighborhoods lit up at once. Clouds collapsed by the thousands, turning cold hydrogen into furnaces of fusion. If you stood on an ancient world during that epoch and looked up, there would be more naked-eye stars than you could count. It was not a quiet universe. It was a construction site. But even at its height, the seeds of decline were being sown. The same inflows that fed young galaxies also triggered pressure waves, shocks, and winds. Starburst bred supernovae, and supernova bred feedback great outflows that heated gas and tossed it into the galactic halo, where it could no longer cool and settle. Creation had a cost, and the bill would come due. Meanwhile, collisions reshaped the landscape. Galaxies merged often, sometimes gently, sometimes catastrophically. In the most violent unions, gas clouds were compressed into a frenzy of starbirth, then blown apart by the very stars they created. Imagine a forest so fertile it grows itself into a wildfire. That was cosmic noon. And yet something even more decisive stirred at galactic centers. Supermassive black holes, quiet regulators in calmer times, woke to feed on streams of gas. Their accretion disks blazed across the spectrum. Their jets drilled through entire galaxies. In moderation, they pruned growth. In excess, they sterilized it. Cosmic noon was glorious, but it was also self-poisoning. So why didn't this engine run forever? Because the universe doesn't just evolve in place. It expands. With every passing eon, the web stretched, densities fell, and the fuel lines thinned. The banquet could not be sustained. Feedback. How the cosmos learned to say no. To make a star, you need three things: gas, gravity, and time. To stop a star, you only need heat. Heat puffs gas up, keeps it buoyant, and denies gravity its grip. The universe discovered this trick early and used it everywhere. Start small. A newborn cluster breathes fire. Massive stars blast ultraviolet radiation and launch winds that sweep a nebula clean. Then they die, some within a few million years, with supernova shockwaves that punch cavities in the interstellar medium. Those holes connect, forming porous chimneys for hot gas to vent. The neighborhood cools more slowly. Fewer clouds collapse. Starbirth slows. Scale up. Entire galaxies surf on feedback. Starbursts launch galactic winds, vast outflows carrying metals and dust into the halo, where they linger like heat haze. Cooling times lengthen. Gas that once fell readily to the disk now stalls in a warm suspension, unable to condense. If the inflow weakens at the same time, say, because cosmic expansion starves the filaments, the galaxy's fuel tank drops below ignition, then there's the black hole veto. Accretion flares heat gas, not just locally but galactically. Radiation pressure shock cones and especially relativistic jets can inflate lobes of hot plasma tens of thousands of light years wide. The energy doesn't create stars, it prevents them, and the paradox deepens. The more massive the galaxy, the more massive the central black hole and the more decisive the shutdown. Dust, the quiet accomplice of star formation, plays both sides. It cools gas, efficiently enabling collapse. But when outflows drag dust into the halo, it becomes part of the insulation layer that keeps gas hot. The same grains that midwife stars become the veil that delays their successors. Feedback isn't a switch, it's a thermostat with hysteresis. Once a galaxy gets too warm, it doesn't cool back quickly. The engine sputters, coughs, then idles. In extreme cases, it stalls altogether. Astronomers call it quenching a cold word for a hot process. So the great paradox arrives. The universe's most productive era built the very tools that ended it. Creation made its own breaks. Red and dead, autopsies of galaxies. Walk the morgues of the cosmos, the giant ellipticals, the massive spheroids, the silent graveyards of stars, and you see a pattern. Their colour has shifted from blue-white to red, a sign that short-lived high-mass stars vanished long ago. What remains are long-lived dwarfs flickering dimly along with the ashes of stellar evolution. White dwarfs, neutron stars, and the dark gravities of black holes. How did these cities of starlight die? Not by a single cause, but by a conspiracy. Repeated mergers choked their centers with gas until the central black hole lit up, sterilized the core, and drove the remaining fuel outward. Cluster environments stripped their reservoirs with ram pressure, a wind made of hot intracluster plasma that peels gas from a rushing galaxy. Others simply exhausted their supply and never got it back. Cosmic logistics failed. The strangest murders leave signatures. Jellyfish galaxies trail tendrils of star-forming knots, proof of stripping in action. Stellar streams arc across halos, fossils of swallowed companions. Radio lobes balloon from the core scars of ancient jets. In some the disk remains, but it's empty of cold clouds. In others even the disk is gone, replaced by a near featureless ellipsoid. Not every galaxy dies young. Some, like our Milky Way, idle at a modest pace, turning a handful of suns per year. But patience is not a cure. The supply lines are thinning and our calendar is long. The cosmic actuarial tables do not lie. All galaxies will age into redness. Some will go quietly. Some will go with a last burst of fireworks. None will shine forever. And yet the autopsy offers more than grief. It offers diagnosis. The universe is past its prime. That's not a metaphor, it's a measurement. The cosmic star formation rate peaked billions of years ago and has fallen ever since. We are witnesses not to the dawn of light, but to its long evening. If that's true, what comes after evening? Does the universe simply dim into sleep? Or is there a deeper betrayal ahead? Dark energy, the expanding silence. Expansion was already the universe's plot twist. Accelerated expansion is its final act. In a cosmos driven by dark energy, space doesn't merely grow, it grows faster with time. Structures that are not gravitationally bound drift apart, redshifting each other into invisibility. The more the universe expands, the more capacity it has to expand. It's a feedback loop with no off switch. What does that mean for galaxies? It means supply chain failure at scale. The filaments that once funneled fresh gas into halos stretch thin. Inflows weaken. Star-forming disks sputter. Even without violent quenching, a galaxy starves. Think of civilization with empty roads. The cities still stand, but the caravans never arrive. On larger scales, dark energy redraws the map. Distant galaxies recede until their light is stretched beyond detectability. The cosmic microwave background continues to cool and fade. The ultimate baby picture becomes a ghost. In the far future, observers in our island group will see only their local bound collection, and nothing beyond. The universe will look small again, not because it is, but because the rest has slipped over a horizon of speed and time. Dark energy doesn't rip stars from galaxies. Gravity defends what is bound, but it does ensure that what's lost stays lost. No fresh gas from outside, no new mergers from afar, only the long accounting of internal reserves. And once those are spent, there is no bailout. So the decline is double. Physics inside galaxies says heat the gas. Cosmology outside says thin the pipes. The combination is devastating, slow, inevitable, and almost polite. The universe dies not with a bang, but with a subsiding breath. But a whisper can carry. In the depths of time, do new wonders arise, rare sparks in the dark? The answer is stranger than it sounds. Long twilight, embers that refuse to go out. Fast-living giants vanish first. It's the humble stars that inherit the future. Red dwarfs, miserly with fuel, can burn for trillions of years, far longer than the universe has currently existed. In the long twilight, they dominate the sky, faint but stubborn like coals that refuse to die. As metals accumulate, star formation itself changes character. Cooling becomes easier, the minimum viable star mass drops. Exotic outcomes appear at the margins. Barely their stars, glowing just above the threshold of fusion, their surfaces cold enough to host frost, their cores warm enough to sip hydrogen for ages. Where binaries of brown dwarfs collide, a true star can flicker on a match struck in an abandoned city. But every ledger balances. White dwarfs bleed their heat into space, sliding toward invisibility. Neutron stars spin down. Black holes feed rarely and quietly unless a stray passerby wanders too close. Entire planetary systems drift apart in slow gravitational pinball ejected into the deep. The fireworks stop, the choreography continues. Against this hush, galaxies still act. The Milky Way and Andromeda merge, then merge again with their companions, forging a single island of stars. The local group becomes a local one, an oval of light floating in an expanding dark. Inside, the last cold clouds form the last modest generations of suns. Outside, silence accelerates. Is this the end? Not yet. Even after star formation ceases, physics remains inventive. Frozen iron hearts, possible exotic fusions, black hole whispers, each a new dialect of light. The universe does not give up easily. It changes the rules of its radiance. But change can be another word for diminishment. Every era illuminates less volume, fewer actors, narrower bands. The grand play becomes a monologue, then a murmur, then a breath. Black holes have always been the accountants of the cosmos, tallying mass and momentum with ruthless efficiency. In youth they regulated galaxies. In middle age they rationed fuel. In senescence they become the final collectors, sweeping up strays, swallowing the unbound, cashing out the last kinetic chips on the table. A quiet black hole is not asleep. It is patient. It waits for gravitational chaos to deliver it crumbs. A wandering dwarf star, a loose gas stream, or an unlucky planet. Each meal flashes a brief flare, then fades to infrared embers. Over absurd spans, central black holes grow even as their cities empty. But even the bookkeepers have a deadline. Quantum fields hum at horizons. Hawking radiation lets black holes leak. The bigger they are, the colder and slower the leak, but time is plentiful in a dying universe. Given enough zeros on the clock, every event horizon unravels. The ledger burns itself. After the last black hole evaporates, the universe enters a weirder quiet. No macroscopic engines, only particle whispers. Whatever complexity persists is held together by feeble forces over ridiculous distances. If there is meaning left, it sits in the statistics of noise. And yet, if we've learned anything from cosmic history, it's that the universe surprises us. It found ways to ignite when it was thin. It found ways to regulate when it was crowded. Might it find ways to shimmer when it's almost empty? Physics hints at possibilities. Rare tunneling events, exotic condensates, improbable fusions in frozen matter. None make a new dawn. Some sketch a longer dusk. A future astronomer will see less. Not because there is less to see, but because horizons move inward. The wider cosmos recedes beyond detectability. The fossil light of the Big Bang fades beyond inference. Without a cosmic backdrop, even the past becomes hard to prove. The universe will look provincial again, an island without charts. Does that mean truth disappears? Not quite. Physics leaves invariance relationships between things that do not rely on distant evidence. Gravity still curves space. Quantum fields still fluctuate. Thermodynamics still tallies loss. But the story grows incomplete. The archive goes dark. That is the final cruelty of a dying universe. It doesn't just dim the lights, it erases the records. Meaning survives where it can be remembered in structures that endure long enough to carry it. Stars once played that role, then planets, then minds. In the very long run, none are safe. So why tell this story now? Because we live in the brief luminous window when the cosmos is both bright and knowable. We can see our origins, model our future, and understand the mechanisms that brought us here. Against a timeline of trillions, our moment is a spark. But it is also a summit, and there is a deeper consolation. Endings give shape to middles. The fact that the universe will die does not make it less magnificent. It makes it precious. The physics that writes the last chapter also wrote the first and everything we love in between. Echoes of the first light. Every ending hides its reflection in the beginning. To grasp how the universe fades, we must return to when it first ignited. For nearly 400,000 years after the Big Bang, there were no stars, no galaxies, only a seething plasma so hot that atoms could not exist. Photons ricocheted endlessly, trapped in an opaque fog. Darkness wasn't the absence of light, it was the imprisonment of it. Then came recombination. Electrons bound to nuclei atoms formed and photons were set free. That release still glows around us as the cosmic microwave background a faint whisper stretched thin by billions of years of expansion. It was the first message, the first signal, the first memory the cosmos left us. But like everything else, it will fade. In 100 billion years it will be too redshifted to detect. The first light will go dark. What followed was stranger still. The cosmic dark ages, hydrogen and helium drifted in expanding space, cold and featureless. No stars lit the void. No galaxies stitched filaments together. If you could have stood in that abyss, you would have heard silence so profound it defies description. And then ignition. The first stars' titans of fusion erupted like beacons. They were nothing like the sun. They were hundreds of times its mass, blazing with ferocity, living fast and dying young. Their supernovae forged the first heavy elements, carbon, oxygen, iron, the raw ingredients for everything to come. But their brilliance was brief. Within a few million years they were gone, leaving only black holes and enriched clouds behind. This was the universe's first betrayal. Creation inseparable from destruction. To make light, it had to ensure death. To seed planets, it had to burn through giants. Every gain was purchased in loss. If the universe began its story this way, sudden ignition, rapid death recycling into the next act, then perhaps its twilight is not a collapse but an echo. Not one death but a rhythm of diminishing cycles. The question is, how many cycles remain? The rhythm of creation and decline. The universe breathes in waves. It does not simply expand, it pulses with eras. The age of first light gave way to the age of galaxies. The age of galaxies gave way to the age of clusters. Each epoch more complex, more structured, and paradoxically more fragile. At cosmic noon, the rhythm reached its crescendo. Galaxies collided, merged, and lit up. For a time, everything seemed to accelerate. More stars, more dust, more black holes feeding. But crescendos do not sustain. Energy disperses, heat accumulates, and order succumbs to entropy. In physics, it's not poetry, it's inevitability. Today we sit in a quieter measure. Star formation in the Milky Way produces only a handful of suns per year. Clusters that once blazed now drift into sedate equilibrium. The rhythm is slowing. Astronomers can graph it. A bell curve of starbirth peaking billions of years ago and declining ever since. We are living on the downward slope, and yet the cosmos resists silence. Even as the pace falls, creativity persists. Stars still form galaxies, still merge, black holes still flare. The universe is not dead, it is dying slowly. And that distinction matters because slow deaths leave room for strange surprises. But this rhythm has a grim conductor, entropy. Each transformation spreads energy. Thinner reduces its usefulness, makes the next act less likely. Entropy does not forbid complexity, it taxes it. Every star pays that tax, every galaxy pays it, and eventually the whole universe will default. So the rhythm is more than history, it's prophecy. The arc from simplicity to brilliance to silence is not unique to life or planets or stars. It is cosmic law, which leaves us with a sobering thought. If the universe itself is subject to this rhythm, then perhaps everything we know is just one brief phrase in a song that is destined to fade. Entropy, the silent dictator. If there is a single law that writes the fate of the universe, it is entropy. Unlike the flamboyant forces of gravity or electromagnetism, entropy is quiet, patient, and absolute. It is the tendency of energy to spread, to equalize, to dilute its own usefulness. When a star shines, it is paying entropy's tax, turning ordered nuclear fuel into a haze of photons. When galaxies collide, they trade their neat orbits for chaotic ones. When black holes feed, they swallow information into horizons that may never return it. Each act of creation is also an act of surrender. On human scales, entropy looks like coffee cooling in a mug. On cosmic scales, it looks like the fading of starlight, the thinning of gas, the darkening of skies. Over trillions of years, entropy doesn't just win, it erases the scoreboard. The universe approaches thermal equilibrium where everything is the same lukewarm nothingness. No gradients, no flows, no engines, no life. This fate has a name: the heat death of the universe. It is not fire but frost, not explosion but stillness. Imagine a cosmos where every black hole has evaporated, every star has cooled, every particle drifts alone in expanding space. Motion continues, but meaning disappears. Some physicists protest. Isn't this too simple? Too final? Perhaps entropy is not destruction, it is redistribution. And sometimes redistribution allows new exotic orders to appear briefly. But entropy never forgets. It is the one account that never forgives debt. The cruelest part: heat death doesn't arrive in a sudden catastrophe. It creeps in increments, stars dying, galaxies reddening horizons, slipping away until the silence is complete. By the time the end is obvious, it will already have been unfolding for eons. Alternate fates, crunch, rip and bounce. The universe may be dying, but the manner of its death is still contested. Heat death is the front-runner, but other candidates lurk at the edges of theory, dramatic, violent and strange. The Big Crunch imagines the universe reversing course. Expansion slows, halts and turns into collapse. Galaxies that drifted apart are dragged back together. Temperatures rise, densities soar, and in the final instant the cosmos implodes into a singularity not unlike the one from which it was born. If true, then perhaps the Big Bang was not a beginning, but a heartbeat in a cycle of births and deaths. But so far, dark energy's acceleration makes this unlikely. The Big Rip is even more terrifying. If dark energy is not constant but grows stronger with time, it could eventually overpower even gravity itself. First galaxies dissolve, then stars are torn from planets, then planets are shredded into dust. Finally, even atoms are ripped apart as space-time itself fractures. The end arrives not in silence but in violence, a universe shredded down to its quantum threads. Then there is the Big Bounce, a phoenix scenario where contraction leads not to finality but to rebirth. Some models of quantum gravity suggest that the singularity of a crunch would rebound into a new expansion. If so, then our universe may be only one cycle in an endless chain. Every death would be a womb, every silence a pause before another crescendo. Each of these scenarios is speculative, but each carries a lesson. We do not know as much as we think. The cosmos hides its cards well. Our measurements today favour eternal expansion and heat death. But a subtle shift in dark energy's nature could flip the script entirely. So the universe confronts us with another paradox. The farther we look, the less certain the ending seems. Twilight has already begun. Look around our night sky. It feels vibrant, endless, eternal. But astronomers measuring the cosmic star formation rate know the truth. The universe's golden age ended billions of years ago. We are not in cosmic noon. We are not even in cosmic afternoon. We are in the evening. Our own Milky Way creates just a few stars each year. That may sound abundant, but compared to its past, it is meagre. 10 billion years ago, galaxies produced stars at a rate 10 times higher. Today, most galaxies are quiet suburbs rather than bustling cities. The light we see above us is largely the light of stars already burning, not the glow of new ones igniting. This is twilight, not metaphorical but measurable. The decline is in progress. Cosmic surveys confirm that the universe is dimming. The proportion of blue star-forming galaxies shrinks. The red quiescent ones multiply. It is as if the universe itself has entered middle age, its vitality ebbing, its energy dispersing. And yet twilight has its beauty. The skies remain full, the constellations familiar. We exist in a rare window where the universe is both old enough to be understood and young enough to remain luminous. That balance will not last. Consciousness at twilight. Why do we exist now and not in some other era? Cosmologists call this the coincidence problem. Out of trillions of years the universe may endure, why are we alive during the brief sliver when stars are still plentiful, galaxies still visible and dark energy only just accelerating expansion? The answer may be selection. Life as we know it depends on the heavy elements forged in stars, but not too many generations in, or they would be locked in dead remnants. Civilizations require stable planetary systems, neither too chaotic nor too sterile. Consciousness blooms best in moderation between the violent dawn and the silent dusk. If that is true, then our existence is a mirror of the universe's own trajectory. We are children of twilight. We arose in the narrow band when the cosmos still burned brightly, but had cooled enough to craft planets, oceans, and DNA. In a very real sense, the universe had to age before it could know itself. But that awareness comes with weight. To know that the universe is dying is to feel a double mortality, our own and the cosmos's. And yet there is wonder too. For the first time in 13.8 billion years, the universe can look back at itself, measure its own decay, and write its own elegy. Reading the universe's medical charts, astronomers are physicians of the cosmos taking its vital signs. They measure redshifts to check expansion count starbirths to track metabolism, observe black holes to gauge stress. The charts are clear. The patient is stable but in irreversible decline. Deep field surveys with the Hubble Space Telescope and now the James Webb Space Telescope reveal the cosmic history of light. They show galaxies small and chaotic in youth, luminous in maturity and tired in age. Simulations like Illustrious TNG and Eagle recreate this arc with millions of virtual galaxies confirming the pattern. A steep rise in star formation, a peak, then a long tail of fading productivity. We can even quantify twilight. At cosmic noon, the universe formed stars at a rate over 10 solar masses per year per galaxy. Today the Milky Way manages just 1 or 2. In a trillion years that number will be 0. The cosmos is not a patient that might recover, it is one moving predictably toward hospice care. But the charts reveal more than decline. They show causes. Feedback loops, dark energy, environmental stripping, quasar activity, all written in the data. The universe is not dying of one disease. It is succumbing to a web of interconnected failures. In a way, it is not dying at all. It is simply completing its growth cycle. The black hole paradox. At the heart of nearly every galaxy lies a monster, a supermassive black hole. For years they were thought to be passive, irrelevant specks compared to the galaxy around them. Now we know the opposite. They are the regulators of growth, the engines of decline, the paradox at the center of it all. When a black hole feeds it, unleashes more energy than billions of stars combined. This energy can sculpt galaxies heating and expelling gas-halting star formation for millions of years. And yet without them, galaxies might have burned their fuel too quickly, exhausting themselves even sooner. Black holes both prolong the cosmic dance and now terminate it. Observations of galaxies like M87 show the aftermath. Jets of radiation stretching thousands of light-years, lobes of plasma marking the crime scene of galactic death. The Event Horizon Telescope captured its silhouette, a black scar against infinity. It looked like the culprit caught in the act, the murder weapon still hot. So we face another irony. The very centers that gave galaxies their order are also the agents of their demise. Creation and destruction are not separate, they are entwined in the same engine. What does it mean for everything to end? It is one thing to chart decline, another to confront its meaning. If all galaxies fade, if all stars cool, if even black holes evaporate, then what remains? Does the universe end in silence, or does it transform into something beyond our comprehension? Entropy suggests finality. Equilibrium, nothingness, no gradients left. But physics often surprises us. Out of plasma came atoms. Out of atoms came stars. Out of stars came life. At each stage, new forms emerge from apparent exhaustion. Could even the death of the universe hide seeds of novelty? Some theorists speculate about quantum tunneling events, vacuum decay or exotic matter states that could give rise to new structures. Others dream of multiverse cycles, each death feeding the birth of another cosmos. But certainty eludes us. The best we can say is that the universe as we know it will end. Its familiar lights, its galaxies, its stars, its planets all will vanish. What remains afterward may not be the universe at all, but something unrecognizable. And yet perhaps that is enough. Knowing that even the cosmos is mortal reminds us of our own fragility, but also of our moment's magnificence. To exist in the brief era when the universe still shines is a gift no future epoch will hold. Earth under a fading sky. From our small blue planet, the decline of the universe is invisible. The sun still blazes, the Milky Way still arcs overhead. Telescopes still collect light from galaxies billions of years away, but every photon we catch is a message from the past, not the present. The farther we look, the younger the universe appears. The present-day cosmos is dimmer than any telescope can directly reveal. Earth itself is caught in a shorter countdown. In 5 billion years, the sun will swell into a red giant, scorching the planet and stripping away its oceans. Long before the heat death of the cosmos, our world will be uninhabitable. And yet Earth is part of the larger story. The fading of fuel, the aging of stars, the relentless arithmetic of entropy. Our night sky is a privilege of timing. Future civilizations, if any survive, will not see what we see. Galaxies beyond the local group will vanish into the accelerated expansion invisible forever. To them, the universe will look empty as if their island were the only one. They may never discover cosmology at all. So we live at a rare intersection. A habitable planet orbiting a stable star in a galaxy, still active enough to study the cosmos while it is young. We are cosmic witnesses standing at the window of twilight, and the view is extraordinary. The longest goodbye. The future of the cosmos is not measured in centuries, millennia, or even millions of years. It is measured in trillions. In that vast calendar, entire civilizations rise and fall in the blink of an eye. Trillions of years from now, red dwarfs will still burn faint but steady. When they finally exhaust their hydrogen, they will fade into black dwarfs, cold embers in the dark. Occasionally, 2 brown dwarfs may collide, striking a brief new spark. But each flare is rarer than the last. After 10 to the power of 20 years, most stars are gone. Galaxies dissolve as gravitational encounters fling their stars into intergalactic exile. Black holes dominate the night, silent collectors of the last matter. Over still greater spans, even they evaporate via Hawking radiation, releasing faint whispers of heat until they too disappear. Beyond 1 Google years, the universe enters a new age. The dark era, no stars, no galaxies, no black holes, only particles drifting endlessly through a space that continues to expand. It is not violent. It is not sudden. It is the slowest, longest goodbye in history. Exotic endings. Physicists are not content with silence. They ask, could the end be stranger than we imagine? Some speculate about iron stars, hypothetical remnants formed when quantum tunneling allows protons in black dwarfs to fuse into iron. These stars would be dark, cold, and nearly eternal, glowing only faintly as they shed their last scraps of heat. Others point to vacuum decay, a catastrophic possibility rooted in quantum field theory. If our universe exists in a false vacuum, it could one day tunnel into a lower energy state. The transition would expand at nearly the speed of light, rewriting physics itself, obliterating all structure. No warning, no survivors, just a sudden change of rules. Then there are ideas even wilder. Boltzmann brains, self-aware fluctuations of matter arising from random quantum noise. If entropy rules forever, then given infinite time, consciousness might appear again by chance. But would that be life, or just the cruelest parody of it? Each scenario is speculative, but each shows the same truth. The cosmos is not guaranteed to die quietly. Its decline may hold surprises stranger than any beginning. Why knowing the end matters? If the universe is doomed, why should we care? because endings give context to beginnings. Knowing the fate of the cosmos sharpens the meaning of our present. We are temporary, yes, but so is everything else. Galaxies, stars, and even space-time itself share in impermanence. To realize this is not despair, it is perspective. Our lives matter not because they last forever, but because they happen now in the thin, luminous band between chaos and silence. For scientists, studying cosmic death is not morbid curiosity. It is the continuation of a journey begun when humans first looked at the stars. For philosophers, it is a reminder that permanence is an illusion. For all of us, it is a call to wonder. In a universe destined for silence, we are the brief symphony of awareness. Full circle. The story of the universe begins and ends in darkness. At the dawn, there was a hot, dense fog, a silence waiting for stars. At the dusk, there will be a cold, thin emptiness, a silence after stars. Between those silences lies everything, galaxies, worlds, life and thought. In that span, light fought darkness. Hydrogen fused to helium, gravity, sculpted suns, chemistry gave birth to biology. Awareness arose, and for a fleeting moment the universe looked back at itself. That moment is ours, so is the universe already dying. Yes, the decline is measurable, inevitable, unstoppable, but death is not the opposite of life, it is its frame. Without it, nothing would matter. With it, everything becomes precious. When the final star cools and the last black hole evaporates, the universe will fall silent once more. But silence is not nothing. Silence is a canvas. Perhaps on it new symphonies may one day be painted, or perhaps not. Either way, we were here in the brightness, in the knowing. This is the story of the dying universe. A story still being written in starlight, and one we were fortunate enough to read before the ink fades forever. Dark matter, the invisible architect of decline. We speak often of stars, galaxies, and black holes, but the largest actor in this story is invisible. Dark matter. It outweighs visible matter by a factor of 5 binding galaxies in its silent grip. Without it, the Milky Way would have unraveled long ago. Yet in the long run, even dark matter cannot save the cosmos. Dark matter shaped the web of galaxies, sculpting the scaffolding on which everything luminous hangs. It guided the first clouds into collapse, seeded the first galaxies, and maintained their coherence. In that sense, it was the midwife of creation. But gravity is impartial. The same dark matter halos that once sheltered galaxies are now stretched thin by dark energy's expansion. Their role is less guardian, more undertaker, and there is a deeper mystery. We do not know what dark matter is. It may be a particle beyond the standard model or a shadow of something more profound. If it decays even slowly, then the universe's decline is not only inevitable but accelerated. In that scenario, the very skeleton of the cosmos crumbles. Imagine the irony. The invisible force that gave galaxies their strength might also dictate the terms of their extinction. If so, then cosmic death is not just written in starlight but in the silence between stars. For billions of years, planets have been the quiet witnesses of cosmic drama. They orbit stars, cradle oceans, nurture atmospheres, and occasionally give rise to life. But what happens to planets in a universe that is running out of fuel? First they lose their suns. Stars like ours will swell, scorch, and shed their outer layers. Some planets will be engulfed. Others will be cast into freezing exile. Around red dwarfs, worlds may endure for trillions of years, but their skies will dim as the stars themselves flicker out. Planets without stars wander the void. Rogue worlds drifting in darkness. Some may carry subsurface oceans heated by radioactive decay or tidal forces, tiny pockets of warmth in an endless night. Could life persist there? Perhaps, but it would be a lonely persistence. Even the planets that remain bound to long-lived stars face slow decay. Tidal forces will drag moons into their hosts or fling them away. Atmospheres will leak into space. Over unimaginable spans, collisions will grind rocky worlds into rubble. Civilizations, if they endure long enough, will face stark choices. abandon their planets for engineered habitats, or find ways to harness dwindling starlight with impossible efficiency, and when the last star fades, even ingenuity may not be enough. Human beings once imagined the universe as eternal. To discover its mortality is both terrifying and liberating. If the cosmos itself will one day perish, then permanence is an illusion, and impermanence is the only constant. This realization has ancient echoes. Philosophers spoke of cycles of fire and rebirth, of worlds rising and falling. Modern cosmology confirms their intuition. Nothing lasts, not even galaxies, not even time itself. The scale is larger, the physics sharper, but the theme is the same. So what do we do with this knowledge? Some feel despair that all efforts are futile if the universe ends. But there is another view, that transience is what gives beauty its sharpness. A flower that never withers is scenery, not miracle. A star that never dies would never see the chemistry of life. A universe that lived forever might never have birthed us at all. Seen this way, the death of the cosmos is not a tragedy. It is the frame that makes existence meaningful. Our moment matters not despite the end, but because of it. Humanity's cosmic diary. If the universe is destined to erase its own records, then memory becomes resistance. Every observation we make, every image from Hubble or James Webb, every equation written on a page is a diary entry against oblivion. We are the first beings, as far as we know, to measure the cosmos with such clarity. We have traced its birth in background radiation, mapped its growth in galaxies, and projected its death into trillions of years. In doing so, we have given the universe something it never had before: self-awareness. But how long will that awareness last? Our digital archives may not endure geological time, let alone cosmic time. Paper burns, servers corrode, even spacecraft decay. Perhaps our best hope is to scatter records across the stars' messages, etched into durable media launched beyond the Milky Way, in the faint chance they survive longer than their makers. Even if no one ever reads them, these records matter. They are proof that for a brief era the universe knew itself. That knowledge is fragile, yes, but it is also luminous. Rebirth in the silence. Is death the end or a transformation? Cosmology does not answer, but it whispers possibilities. Some theories suggest that our universe is one bubble among many, and that when ours fades, another may ignite. Others propose cycles: expansion, followed by contraction, collapse, followed by rebound, a heartbeat across eternity. Still others hint at quantum fluctuations, where even in the emptiest dark, new sparks may appear. We cannot prove these ideas. We may never prove them, but they remind us that the universe has always been stranger than expected. Who foresaw atoms in plasma, or galaxies in chaos, or life on a rocky world orbiting an average star? Perhaps the end is not final but fertile. Perhaps silence is not nothing but a canvas for another story. And even if that story never comes, our own was still written in stars, in minds, in memory. The universe is dying, but in its dying it has birthed the most improbable thing of all: awareness that it is dying, and that awareness is ours. Life in the long night. When the stars fade, what becomes of life? For now we know it as fragile, bound to light and warmth. But in a darkening universe, the definition of survival must expand. Some speculate about civilizations around red dwarfs, tiny suns that can live for trillions of years. These stars burn so slowly that their planets may enjoy stability far longer than Earth ever will. If intelligence arises there, it may witness epochs beyond our comprehension. But even red dwarfs have an end. Other scenarios are stranger. Rogue planets with subsurface oceans could shelter microbial life warmed not by sunlight but by internal heat. Could such life persist for billions, even trillions of years hidden in icy shells, while the galaxy outside grows silent? If so, life might never completely vanish, it would only retreat waiting in shadows. But intelligence demands energy. Civilizations need more than scraps of heat. They need power to think, to build, to dream. In the long night, energy becomes the rarest currency of all. The cosmos itself conspires against endurance, leaving the question open. Can life outlast its stars, or must it surrender to the silence? Dreaming beyond limits. Humanity has always resisted boundaries. Oceans, mountains, and skies were once barriers. Now they're pathways. But the limits written into the universe are different. They are not logistical, they are fundamental. The speed of light, the scarcity of fuel, the inevitability of entropy. These are not walls to climb, but laws to obey. Yet dreamers persist. Some imagine building Dyson spheres around stars, harvesting nearly all of their energy. Others imagine moving stars themselves, dragging suns into safe harbors to extend their lifetimes. In the far future, advanced civilizations might learn to tap exotic sources. Black hole spin, quantum fluctuations, or even the decay of dark matter. But here is the paradox. Every strategy still bows to entropy. Energy cannot be created without cost. At best, we can delay the inevitable, we cannot erase it. The universe is not a puzzle we can solve, but a stage we can perform upon until the lights dim. Still, perhaps that is enough. To live longer, to know more, to carry awareness farther into the abyss. This is not immortality, but it is defiance. And defiance too is meaning the horizon of knowledge. Knowledge is light. It pushes back darkness, reveals patterns, and tells us where we are. But knowledge, like light, has a horizon. In a universe that expands forever, that horizon creeps inward until much of reality slips beyond reach. Future astronomers will see fewer galaxies, not because they vanish, but because their light will never arrive. The cosmic microwave background, our oldest record, will fade into nothingness. Even the fingerprints of expansion may grow too faint to measure. At some point, observers may conclude they live in a small static cosmos. The truth will be gone, not because it changed, but because it escaped observation. So there is a cruel irony. We alive today may be among the very few generations in all of cosmic history capable of knowing the universe's true story. We arrived at twilight, yes, but twilight is the moment when the horizon is widest, when the view is richest. We live in the golden hour of knowledge, but even now mysteries persist. Dark matter, dark energy, quantum gravity. Our picture is incomplete. If knowledge has a horizon, perhaps we will never see the full portrait. And yet maybe that incompleteness is the point. Curiosity is not diminished by limits, it is defined by them. Our place in a mortal cosmos. For thousands of years humans wandered about the heavens. Now we know the heavens are mortal too. That knowledge is humbling, but is also empowering. Because it means the universe is not a cold, eternal backdrop, it is a partner in our story. We are stardust, yes, but we are also starlight, brief and brilliant. Our thoughts, our art, our questions, all are temporary flashes in a temporary cosmos. And that makes them more valuable, not less. What we do in our finite moment becomes our answer to the infinite. Civilizations may fall, worlds may perish, galaxies may fade, but the fact that awareness ever arose at all is a triumph against odds so immense they almost defy language. Even if the cosmos ends in silence, the song has already been sung. Perhaps our purpose is not to escape mortality, but to embrace it fully. To marvel, to understand, to record, and to love, knowing all the while that will not last. That fragility is the source of beauty, the miracle of now. The universe is dying. The evidence is clear, the timeline inevitable, and yet look around. The stars still shine, the galaxies still wheel overhead, the Earth still hums with life. The miracle is not in what will happen trillions of years from now. The miracle is that we are here now, able to see it, to know it, to wonder at it. Mortality gives meaning to every sunrise, every discovery, every fleeting joy. A cosmos without death would also be a cosmos without urgency, without story, without us. The fact that it ends is the reason it matters, so let us not mourn the universe's fate. Let us marvel that in its vast unfolding there came a time when hydrogen burned into stars, forged heavier elements, planets formed, and one of those planets asked, "What will become of it all?" This is our moment. This is our window. And though the lights will one day go out, the wonder they inspired will remain for as long as we carry it and perhaps beyond. The universe may end in silence, but in us for now it speaks. Epilogue, the elegy of a mortal cosmos. The universe is vast beyond comprehension, yet fragile in its fate. For centuries humanity gazed at the stars, believing them eternal, believing the heavens to be the stage of gods or the machinery of forever. Today we know better. We know the cosmos is not timeless marble, but living fire, and like all fires it will burn down to embers. This knowledge is both humbling and electrifying. On one hand, it strips away illusions. There will be no infinite sky, no everlasting galaxy, no immortal suns. Every star will cool, every planet will freeze, every atom will drift apart. The great structures of the cosmos, spiral arms, clusters, filaments, will collapse into silence. In time, even the black holes, those final sentinels of gravity, will evaporate into whispers of heat. On a long enough timeline, the universe becomes indistinguishable from nothing. On the other hand, this truth amplifies the significance of now. Consider the odds. 13.8 billion years of cosmic evolution, countless accidents and collisions, an immeasurable ballet of atoms, and in this fleeting moment, we are here. We can see galaxies at the edge of visibility. We can hear the echo of the Big Bang in microwave radiation. We can chart the future until the last light fades. We can know that knowledge itself is a miracle. Think of what that means. Stars do not wonder if they will die. Black holes do not contemplate their own evaporation. But we do. In us, the cosmos has developed the rarest of faculties. The ability to reflect, to ask questions, to wrestle with inevitability. Awareness is not an escape from mortality. It is the flowering of it. Without death, awareness may never have existed. So perhaps the universe's ending is not tragedy, but culmination. It is the final chapter of a story that was always finite, always precious, always improbable. When the last star cools, the last photon fades, and the last black hole evaporates, there will remain only one undeniable fact, that once against all odds the universe knew itself through us. And maybe that is enough. Maybe the meaning of a mortal cosmos is not to last forever, but to be noticed, to be understood, to be cherished while it burns. When future civilizations, if any, endure, look back at this brief era of brightness, they may marvel that the universe ever achieved such clarity of self-reflection. For us, the lesson is simpler. Live as though every moment is as rare as a star, because it is. Every sunrise, every discovery, every act of wonder is a defiance of silence. We are the universe's way of celebrating its own fragile light. So when we ask, is the universe already dying? The answer is yes, but it is also still alive, still radiant, still telling its story in the language of starlight. We are part of that story. We are the witnesses, the recorders, the brief symphony before the long silence. One day silence will come, but today the stars still shined. And while they do so, do we? Could our universe with its billions of galaxies exist inside a black hole? This question, once purely theoretical, now drives cutting-edge research in astrophysics. To explore this idea, we need to understand what a black hole is, and how our universe might mirror its structure. Let's break it down clearly and systematically. A black hole is a region where gravity is so strong that nothing escapes, not even light. It forms when a massive object like a dying star collapses into an incredibly dense point. This point, called the singularity warp spacetime, the four-dimensional grid that defines how objects move and time flows. Picture spacetime as a network of coordinates, not a physical surface twisted tightly around the singularity by its immense mass. The boundary of a black hole is known as the event horizon. This invisible sphere marks the point where gravity becomes absolute, Anything crossing it from a starship to a beam of light is drawn inward with no chance of return. The event horizon's size depends on the black hole's mass. For example, a black hole with 10 times the mass of another has an event horizon 10 times larger, as calculated by the Schwarzschild radius formula. Now let's look at our universe. It has its own boundary called the cosmic horizon. This is the farthest distance from which light can reach us given the universe's age of about 13.8 billion years. Light travels at 299,792,458 meters per second. Beyond the cosmic horizon, roughly 46.5 billion light-years away, light hasn't had time to arrive due to the universe's expansion. Here's the key connection. The observable universe contains an estimated 1.5 times 10 to the 53rd power kilograms of mass, including stars, planets, gas, and dark matter. If this mass were compressed into a black hole, its event horizon would span about 46.5 billion light-years, nearly matching the cosmic horizon's size. The universe's average density, approximately 1 times 10 to the minus 27th power kilograms per cubic meter, also aligns with the density of a black hole of that scale. This match is not trivial. It suggests our universe's structure resembles a black hole's. The question is whether this is a coincidence or a clue to our origins. To investigate, we must delve deeper into black hole physics and examine evidence from our cosmos. This hypothesis, grounded in observation and mathematics, sets the stage for a profound scientific inquiry. The idea that our universe might exist inside a black hole hinges on advanced physics. Albert Einstein's theory of general relativity describes how mass and energy shape space-time. Inside a black hole, this shaping becomes extreme. Past the event horizon, space-time curves so tightly that it forms a new region separate from the outside universe. This region acts like a distinct cosmos with its own rules and structure. If our universe is inside a black hole, we could be living in this isolated space-time. The event horizon would shield us from the external universe, making it impossible to see beyond. Our observable universe, defined by the cosmic horizon, might be the interior of this black hole. This model suggests our reality emerged from a black hole's core, a concept supported by mathematical solutions in general relativity. To understand this, consider how general relativity works. It treats gravity not as a force but as a curvature of space-time. Massive objects like stars bend this grid, causing nearby objects to follow curved paths. In a black hole, the curvature is so intense that all paths lead to the singularity, a point of infinite density. Beyond the event horizon, however, equations predict a new space-time potentially vast enough to house a universe like ours. Recent research offers clues to test this hypothesis. Astronomers have studied the rotation of spiral galaxies which resemble spinning pinwheels of stars. A study examined several hundred galaxies using telescopes to observe their motion. The findings were unexpected. About 2 out of every 3 galaxies rotated in a direction opposite to our Milky Way galaxy. This pattern was seen in observations above and below the Milky Way's plane. This rotational bias is significant. In a typical universe, galaxy spins should be random, with half rotating one way and half the other. A 2/3 preference suggests a coordinated motion across vast distances. This could indicate that the entire universe has a net rotation, a property described as angular momentum. Angular momentum measures how much an object spins and in what direction. Why do galaxies spin at all? When galaxies form, they start as clouds of gas and dust. As these clouds collapse under gravity, any small motion within them grows stronger. This is due to a law called conservation of angular momentum. A large, slowly moving cloud becomes a smaller, faster spinning galaxy. This explains why individual galaxies rotate, but a universe-wide rotational pattern is harder to explain. If the universe has a net rotation, it challenges standard models. The Big Bang theory assumes the universe expanded evenly in all directions with no preferred spin. A rotating universe suggests a different origin, possibly tied to a black hole. This connection is intriguing, but requires more evidence to confirm. The discovery of a possible universe-wide rotation raises deep questions. In most cosmic models, the spins of galaxies should be random. Each galaxy forms from a collapsing gas cloud with its own unique motion. These motions, driven by turbulence, typically cancel out across the universe. A net rotation, where galaxies prefer one spin direction, suggests an unexpected order. This finding challenges our understanding of the universe's origin. Angular momentum is the key concept here. It describes how much an object rotates and in what direction. For example, a spinning top has angular momentum which keeps it upright. In the universe, every rotating object from planets to galaxies carries angular momentum. This property arises during formation. As a gas cloud shrinks, its rotation speeds up, much like a dancer pulling in their arms to spin faster. This is called conservation of angular momentum. In a typical universe, the angular momentum of galaxies should balance out. Half should spin one way, half the other, with no overall preference. The recent study of several hundred spiral galaxies found otherwise. About 2 out of every 3 galaxies rotated opposite to the Milky Way galaxy. This bias observed across vast distances hints at a universe with net angular momentum. Such a pattern is not expected in standard models like the Big Bang, which assumes uniform expansion in all directions. This rotational bias connects to the black hole hypothesis. Black holes preserve only 2 properties from the matter they consume: mass and angular momentum. When matter falls into a black hole, its rotational motion contributes to the black hole's spin. A black hole with significant spin carries a net angular momentum, which could influence the spacetime inside it. If our universe formed within a rotating black hole, it might inherit this spin, causing galaxies to align in their rotation. The idea is compelling but complex. In a rotating black hole described by the Kerr solution in general relativity, the internal spacetime differs from a non-rotating one. The spin creates a dynamic environment, potentially shaping the universe within. The observed galactic rotation could be a remnant of this inherited angular momentum. The universe's mass estimated at 1.5 times 10 to the 53rd power kilograms, and its density about 1 times 10 to the minus 27th power kilograms per cubic meter, already align with a black hole's properties, strengthening this link. The evidence for cosmic rotation is preliminary. The study analysed only a few hundred galaxies, a small fraction of the billions in the observable universe. Larger surveys using advanced telescopes like the James Webb Space Telescope are needed to confirm this trend. If the rotational bias holds, it could reshape cosmology. It would suggest our universe's origin involves a mechanism like a black hole that imparts coordinated motion across cosmic scales. This hypothesis remains speculative but testable. Future research will measure galaxy spins across wider regions and refine our understanding of angular momentum in the cosmos. For now, the possibility that we live inside a spinning black hole offers a fascinating challenge to science, blending observation with bold theory. The hypothesis that our universe exists inside a black hole relies on advanced theoretical models. General relativity, developed by Albert Einstein, provides the framework for these models. It describes gravity as the curvature of spacetime, a 4-dimensional grid of coordinates. In a black hole, this curvature becomes extreme, creating a region where normal physics breaks down. To understand how a universe could form inside, we need to explore specific black hole models, particularly those that account for rotation. Most discussions of black holes start with the Schwarzschild solution, which describes a non-rotating black hole. This model predicts a singularity at the center surrounded by an event horizon. However, the universe's possible rotation suggested by galactic spin patterns points to a different model, the Kerr black hole. Named after physicist Roy Kerr, this solution describes a rotating black hole. Its spin alters the space-time structure, creating a more complex environment inside the event horizon. In a Kerr black hole, the singularity forms a ring, not a point, due to the rotational motion. This ring singularity is surrounded by a region called the ergosphere, where space-time is dragged along by the black hole's spin. Beyond the event horizon, general relativity predicts the possibility of a new space-time region. This region could be vast, potentially containing an entire universe. If our universe formed within a Kerr black hole, its net rotation could be a legacy of the black hole's spin, explaining the observed galactic alignment. Another key feature of our universe is its expansion. Observations show that galaxies are moving apart, with the distance between them increasing over time. This expansion, discovered by Edwin Hubble in the 1920s, is measured by the Hubble constant, roughly 70 kilometers per second per megaparsec. This means that for every 3.3 million light-years of distance, galaxies move apart at 70 kilometers per second. In a black hole universe model, expansion is a critical puzzle. Standard cosmology explains expansion as a result of the Big Bang, where space itself began stretching 13.8 billion years ago. Inside, a black hole expansion could arise differently. Some theories suggest that the new space-time region within a black hole undergoes a rapid stretching mimicking cosmic expansion. This stretching could align with the universe's observed density, about 1 × 10 to the -27th power kilograms per cubic meter, and its size roughly 46.5 billion light-years across. The Kerr model adds complexity to this picture. A rotating black hole's internal dynamics could influence the rate of expansion, potentially imprinting a rotational bias on the emerging universe. The fact that 2 out of every 3 spiral galaxies rotate in the same direction as found in recent studies supports this idea. This rotational coherence, combined with the universe's mass of 1.5 × 10 to the 53rd power kilograms, strengthens the black hole hypothesis. These models are speculative but testable. Astronomers can use telescopes to measure the universe's expansion rate, more precisely looking for signatures of a black hole's influence. Theoretical physicists are also exploring how a Kerr black hole's properties like angular momentum could shape a universe's evolution. These efforts bridge observation and theory, pushing us closer to understanding our cosmic origins. Testing whether our universe exists inside a black hole requires precise observations. The hypothesis hinges on evidence like cosmic rotation and density alignment. To confirm or refute it, astronomers use advanced tools to study the universe's structure and motion. These methods include galaxy surveys, gravitational wave detection, and cosmic microwave background analysis. Each approach offers unique insights but faces significant challenges. The claim that 2 out of every 3 spiral galaxies rotate in the same direction needs broader confirmation. Current studies based on a few hundred galaxies are a small sample of the billions in the observable universe. Large-scale galaxy surveys conducted with telescopes like the James Webb Space Telescope can map the spins of thousands of galaxies. These surveys measure light patterns to determine rotational direction, revealing whether the universe has a net angular momentum. The challenge lies in scale and precision. Observing distant galaxies requires long exposure times, and dust clouds can obscure spin patterns. Surveys must also cover regions far beyond the Milky Way galaxy to avoid local biases. Future projects like the Vera C. Rubin Observatory aim to image millions of galaxies, providing data to test the rotational bias. This could strengthen or weaken the black hole universe model. Gravitational waves, ripples in space-time caused by massive objects, offer another test. Detected by observatories like the Laser Interferometer, Gravitational Wave Observatory. These waves reveal events like black hole mergers. If our universe formed inside a rotating black hole, its spacetime might carry subtle wave signatures from the parent black hole's spin. These signatures could appear as a background hum in gravitational wave data. Detecting such signals is difficult. Gravitational waves from cosmic events are faint and distinguishing. A background signal requires extreme sensitivity. Current detectors focus on nearby events, but next-generation observatories like the planned Laser Interferometer Space Antenna could probe deeper cosmic signals. These advancements may uncover clues about the universe's origin, supporting or challenging the black hole hypothesis. The cosmic microwave background, or CMB, is the universe's oldest light dating back to the Big Bang 13.8 billion years ago. It carries information about the universe's early structure. If the universe has a net rotation, this might appear as a slight twist in the CMB's temperature patterns. Satellites like the Planck Observatory have mapped the CMB in detail, but no clear rotational signal has been found yet. Analyzing the CMB for rotation is complex. The signal, if present, is likely very weak, buried in noise from other cosmic processes. New analysis techniques using artificial intelligence are being developed to search for subtle patterns. These efforts could reveal whether the universe's expansion measured at 70 kilometers per second per megaparsec aligns with a rotating black hole's dynamics. Each method faces limitations, but together they build a stronger case. The universe's mass, about 1.5 times 10 to the 53rd power kilograms, and density 1 times 10 to the minus 27th power kilograms per cubic meter, already suggest a black hole-like structure. Confirming cosmic rotation or detecting unique space-time signals would bolster the hypothesis. For now, these observational challenges highlight the need for more data and innovative technology. The idea that our universe exists inside a black hole is bold, but it's one of many theories about cosmic origins. Cosmology offers several competing models, each attempting to explain the universe's structure expansion and features like its rotational bias. Comparing these alternatives to the black hole hypothesis helps us understand its strengths and weaknesses. Let's examine three prominent theories: the multiverse cyclic cosmology and inflationary cosmology. The multiverse theory suggests our universe is one of many, each with its own laws of physics. These universes could exist in separate space-time regions, like bubbles in a vast cosmic foam. In some multiverse models, black holes in one universe could spawn new universes aligning with the black hole hypothesis. Our universe, with a mass of 1.5 times 10 to the 53rd power kilograms, might be one such bubble born inside a parent black hole's event horizon. The multiverse explains the universe's fine-tuned properties, like its density of 1 times 10 to the minus 27th power kilograms per cubic meter. However, it struggles with testability. No direct evidence of other universes exists, and detecting them may be impossible due to their separation from our space-time. The black hole hypothesis, by contrast, ties to observable data like galactic rotation, where 2 out of every 3 spiral galaxies share a spin direction. Cyclic cosmology proposes that the universe undergoes repeated cycles of expansion and contraction. Each cycle begins with a Big Bang and ends with a collapse, followed by a new Big Bang. This model could explain the universe's expansion measured at 70 kilometers per second per megaparsec without requiring a black hole. A rotating universe might arise if angular momentum persists across cycles passed from one phase to the next. Cyclic models face challenges in explaining the universe's current acceleration driven by dark energy. Observations show galaxies moving apart faster over time, which conflicts with the collapse phase of cyclic cosmology. The black hole hypothesis avoids this issue, as its internal spacetime could stretch indefinitely, mimicking our observed expansion. The Kerr black hole spin discussed earlier also better accounts for the rotational bias in galaxy spins. The standard model of cosmology includes inflation, a rapid expansion in the universe's first moments 13.8 billion years ago. Inflation explains why the universe appears flat and uniform with galaxies spread evenly. It assumes a Big Bang origin followed by a brief explosive growth. This model doesn't naturally predict a net rotation, making the observed galactic spin pattern, where 2 out of every 3 galaxies align, harder to explain. The black hole hypothesis offers an alternative. A rotating Kerr black hole could imprint angular momentum on its internal universe, causing coordinated galaxy spins. Inflationary models rely on a hypothetical field called the inflaton, which lacks direct evidence. The black hole model, while speculative, leverages known physics like general relativity and aligns with the universe's size, roughly 46.5 billion light-years across. Each theory has merits, but the black hole hypothesis stands out for its connection to observable data like rotation and density. Multiverse and cyclic models are less testable, while inflation struggles with rotation evidence. Future observations using tools like the James Webb Space Telescope could tip the scales. For now, the black hole universe remains a compelling contender in the quest to understand our cosmic roots.